Hello and welcome to Machine Learning from Data. This is lecture 22, and in this lecture, we will address certain issues pertaining to neural networks, in specific overfitting. So we'll talk about neural networks and overfitting. Foundations come back again in the form of approximation versus generalization. And we'll see that regularization is a useful tool along with early stopping. We'll also see how we can minimize E in efficiently, especially when we are using gradient descent, because we'll see that there are so many issues that accompany this optimization in general. For example, local minima when fitting the data and the algorithm not working as efficiently as we would like to. And so that's something that we look at. So these are like some of the topics for today's lecture. Let's recap what we did in the previous lecture. We did quite a lot, I would say. So we saw how to fit data using neural networks at a basic level. We began with some given set of weights that was like this, like choose some weights to minimize E in, and then got our edge of X, finally like output that we desired, the desired output edge. And well, the forward propagation algorithm worked in that way, right? First, you begin with something based on certain weights, you compute the input, do the transformation, get the output, make it go as an input to the next layer, and so on. All right. So that was the forward propagation algorithm. And then we answer the question of how to get the weights, right? And the quick answer to that was like choose all the weights such that you can minimize the in sample error. And then we figured that it wasn't as trivial as it sounded, and it was like non-trivial because it involved computing gradient of a function that does not have a concrete mathematical definition, which was my h of x, right? So this minimization wasn't as simple as we thought it would be. And forward propagation was an algorithm, like it was an algorithmic way of getting h of x. And so we came up with something that was known as back propagation here, in which we exploited what we were getting, like the outcome of my forward propagation, right? So this backward propagation, what was doing was like we have this gradient of the error with respect to the weights, which has this form, and of course we derived this form, which is like the output from the previous layer times some sensitivity. That delta was the sensitivity. And we figured that that sensitivity was recursive in the sense that we could establish a relationship between my delta in layer L and my delta in L minus 1. So having said that, we began with the last layer and kept like propagating the sensitivity backwards, right? And then you were like ready to implement this model, right? So we learned like uh, that with this backward propagation, we can figure out a way to get the parameters that we needed for this model. Now, next we also looked at like the neural network implemented on digits data, right? And in specific, we looked at this kind of a comparison between gradient descent and the stochastic gradient descent. And what were the differences? As we saw, stochastic gradient descent converges really quickly as compared to gradient descent. And this issue will come back again in today's lecture. The problem that we're beginning to talk about is this here. And as you can see, and that's the goal for today, to address overfitting in neural networks. And can EN be minimized more efficiently? Because we saw this issue coming up, although like neural network really worked well with the digits data, but we saw that there was this lot of overfitting, which is not good. We know that from our knowledge of foundations, right? And so we will address that. So let us begin. We are beginning to talk about a very simple neural network, which is just like a two-layer neural network. And in fact, just like a single hidden layer here. So this is my hidden layer. And in practice, of course, we never work with such a simple model, but this will help us realize a lot of properties of the neural network and how can we work towards generalization versus approximation, right? So each node here in this hidden layer, right, it represents, or I would say implements a perceptron. We know that, right? And this is my input. And maybe imagine that this is not just like one node, but like the set of inputs. That's the input layer that we don't really refer to as much because we know that that's not exactly a part of the neural network. But regardless, these V's here are the perceptrons that I'm talking about, right? So these are my perceptrons. And then we come to the hidden layer, whatever happens here, the transformation, and finally the other weights are applied and we get the output, and this is my output, which is h of x. All right, and so this is my output layer, which again might have applied some theta depending on whatever activation function we have. Okay, so let us assume we have like these m nodes in the hidden layer, m nodes in the hidden layer, and the input is like d-dimensional. So this is what we're going to like continue with going forward. And so what is happening in this layer here? What exactly is happening? Well, we're like transforming whatever the perceptrons were here and then multiplying them with the weights, right? This is what's happening. So essentially what I'm getting at each of for each of these W's is that, let's say for the first one, which is like W1, and the W0 will stay, of course, but W1 times the theta, whatever transformation we did to my perceptron from the previous layer, right? This is what's happening. And then W2 theta V2 transpose X, and so on up to Wm. Let's say there were like m of these, of course. Theta Vm transpose X, right? This is exactly what's going on here. And so we can put all of that together in order to get my h of x, which is nothing but like whatever theta was applied here times the, not really times, like this applied to this like a function essentially. And this is like my W0 based on the bias or the augmented value plus the sum of all of these. So that's what I'm getting here, right? The sum of all these terms. And this in itself is the neural network. This entire thing is a neural network. Of course, I would say a simple variant of a neural network. All right, so why is this equation so important to us? Well, we are trying to, or maybe we are beginning to try to compare this with other models that we have seen before. So what are some of the other models that we have seen before? Right. So one of the other model that we have seen before is the linear model, if you remember. And so in the linear model, we applied some non-linear transform. And let me maybe write somewhere here. So then phi of x, right? My phi of x used to be some like augmented, and then phi 1 of x, phi 2 of x, and so on to phi m of x, right? And then depending on the problem type, this model was like in the z space, some transformation applied to these weights, right? All the weights times these phis, whatever we decided they were, right? And then just like sum them up. So this was my non-linear transformation for my original initial linear model, the basic linear model that we've seen before. All right, there is another model that we've seen before. That's the radial basis function network. And instead of like the phi, we had the kernel. The phi was my kernel. Again, it was nothing but just like representing the functions that we were working with, the bumps, right? And then we had another parameter mu j, which was based on some similarity. What are the centers? What were the centers that we were like interested in? And so essentially this part here, and maybe like there was that divided by r, which is missing here, right? This part here was based on like features that were like similarity based, correct? And let's say what is this k equals like the number of bumps, and maybe we can tell that this k is like, maybe let's say k equals m to have like consistency throughout. And here it's like if the perceptrons were like then my input data was d-dimensional, so let's assume that this is also m, so in order to maintain consistency. And well, this is my radial basis function network. Now if you look at all three of them, like the neural network, the nonlinear transform for my linear model, and my k radial basis function network, right? What is that like striking thing that you see? Well, there is a similarity amongst these three models. They are basically linear models, I would say. They are nothing but all of them are linear models, at least linear in the parameters, except this one here, which like the mu j's are non-linear. We know that, of course. And somehow when we're working with this model, we do consider it as like something that's already known. So there's like that unsupervised pre-processing step that takes place, and then we utilize that model, right? So basically, like in a higher level sort of way, we can say that they are linear models. implemented in some space. For example, Z space for this one, and then maybe similarity based for this one. But yeah, with their differences, they look pretty similar. So based on like just by looking at the way they are expressed in terms of the final hypotheses or like the hypothesis set that we're looking at here, of course they're similar, but then there are differences as well. And what are those differences essentially? So the differences are, if you think about the linear model with the nonlinear transform, I'm talking about this one here, right? We were focusing on picking the function or the transform, which is my phi, if you remember, before looking at the data. We didn't know like which polynomial I want to pick. And like I picked it regardless of the data, right? And that helped me get a relationship, a good relationship between E in and E out, right? So it got me a tight relationship between E in and E out because of all the theory that was involved. All right. What about the radial basis function network? This one. What do we know about it? Well, here there is some level of complexity added because we didn't know how to get similarity based features until we know the centers, as I said, like until we know the mu j's. And so we needed the mu j's. And we, of course, looked at the data. We didn't know the y's, but we looked at the data. We used some unsupervised learning approach where we were able to pick those mu j's, right? And some similarity based measure was used depending on the data distribution. And in some ways we had like some access to the data, which means I have like a slightly more fitting like feature transform here, right? In the sense that I have some knowledge of the data, and so I have that in this situation. Now, what is happening in my neural network? What is happening here? Well, in my neural network, the feature transform is the perceptron, right? For example, this Vj, the Vj's are the perceptrons, right? They are analogous to my Phj's in my nonlinear transform here, right? The Vj's and the Phj's are like somewhat similar. I'm implementing my perceptron here. So I'm trying to optimize the weights, W's, by fitting them to the data and using whatever technique we're using. Let's say we use gradient descent and backpropagation. So we are going to fit the features to the data such that our feature transform fits the data. So there is a huge level of like flexibility that comes in with this, right? My feature transform should fit the data. Okay, fits the data. And my VJs, the perceptrons themselves, are optimized to fit the data, just like the W's were in my linear model. So therefore, my features actually fit to the data, if you think about it, right? So picking features, like or fine-tuning features to fit the data is what's happening in my neural network. And that is giving it the power that it has, right? In my linear model, I did not have like any fine tuning possible. In radial basis function, yeah, maybe a little bit of fine tuning of features was possible. And it has given us like all the power that we can utilize to actually fit like the entire, like I can pick the features based on the data, right? And that's what exactly is happening. And that's why this leads like the neural network to be such a powerful model. And because it's so powerful, we need to like control this power somehow, because that power that this is offering is leading to the issue of overfitting. And so before we talk about overfitting, we need to understand the approximation capability of my neural network. All right, so that's given here, by the way, and this is for a regression problem in general. So for regression and for classification, it's of the order 1 over square root m. And this is telling us that if we increase the number of nodes, what is m? M is my number of nodes in my hidden layer. So this is telling me that if I keep increasing the number of nodes in the hidden data, like in the hidden layer, I will exactly fit the data, right? This is what it's telling me. And this is what was coming out of this equation as well. And so it's a very powerful result because we can like fine tune my features based on this. And like on the other hand, if you talk about the linear model, if we increase the power of my feature transform here, make it more and more complex, I may not be able to fit the data because I picked that before looking at the data. I picked my transform before looking at the data. So I might not be able to, right? For radial basis functions, we saw some part of the data, like the values only. So maybe we'll not be perfectly able to fit the data, like with similarity features, unless like you give me a lot of centers. Maybe you have like huge number of mujs, and so yeah, of course I'll be able to fit the data. But with the neural network, you can see that this comes in, like when we talk about the approximation capability, we can see that we can fit the data as we increase M. Okay, so what next then? What next? Now we have to see how we get a link from my E in to E out, because we haven't discussed generalization of neural networks, right? So let's look at that. Generalization is something that we haven't talked about yet. And by the way, my h of x, I just like want to rewrite it, is the theta of w0 plus the sum of all the m's, which is my node, wj theta vj's are the perceptrons in the very first input layer. And all right, so this is what I have. And what I'm looking at here is first the MLP, or the multi-layer perceptron, right? And the second thing I'm looking at is tan H function. So what are these? Well, these are the activation functions that we used in our neural network. So if my theta, or my activation function, is a sine function, then most likely I'm talking about the multi-layer perceptron. And when we're talking about, and this is like a two-layer perceptron, like we'll, of course, this generalizes to all different layers, but then here we are talking about a two-layer MLP. All right, so the VC dimension of this MLP is of the order MD log MD. And it's possible to derive this. We look at like a high level derivation of this, of course, but what it's telling us is that with like m perceptrons times d input dimension, this is what can be shattered. We can shatter this, right? So what is happening here? Here, like in a perceptron, or like maybe in a neural network rather, right? You have like this cascading like linear models, right? You have these cascading linear models. And maybe this cascading can be compared to taking the union of multiple hypotheses. If you remember in one of the homeworks, we took the union of many hypotheses sets, and each of the m perceptrons had a VC dimension of d plus 1, and so it increased. It increased by some like, we increased the VC dimension logarithmically, and so the order was d plus 1 log m, right? In cascading, it goes like even further depending on my theta, right? And so it can even go to order like md, which is huge. So that's the power of cascading, and that's why because of this like VC dimension, that's why we can see the power of like my neural network in general. All right, a quick overview. If we are using tan H transform, then the VC dimension is of the order MD, M plus D, which is like cubic, quadratic, or even higher. And that's because tan H is more powerful than MLP. In fact, like all the dichotomies that can be implemented by MLP are included in my tan H. So like think of that as a superset of what my MLP can do. And of course, there are other more advanced functions as well. But let's see what we can infer from this like information, the VC dimension, right? Can we choose like, or maybe thinking about like, how is this M impacting my, can we like do something with this M to get a good generalization? And well, in theory, M equals square root of N is a good choice. And why is that? Let's look at that, and then also discuss like the VC dimension of a cascading, like VC dimension of essentially MLP in general. So we'll discuss both of them. First, let's look at like this M equals square root of N. Okay, so my E in for regression is of the order 1 over M, and also my E in is of the order 1 over square root of M. And from our analysis, we already know our foundations. We know that E out is related to E in plus the error bar, which is of the order, I think it was VC dimension n log n. All right. Now, if m equals square root of n, right, theoretically speaking, my E in will be almost like close to 1n or 1/4, right? And my second term here, this thing will also be of the order somehow like close to 1 over n4, close to that, sorry, n1/4, right? And because like I selected my n such that this is what I'm using now. And so if we try to get one of these smaller, the other one will go up. So because E out is like the sum, and hence there will be a trade-off, right? So in theory, we are trying to achieve some or get to some E out, which is like the optimal, the best that we can do. And if there is no noise in the data, then the best we can do is to get this E out close to 0, provided there is no noise. And like my m equals square root of n is able to kind of do that. So this is a classical technique in theory in order to get E out close to 0, right? By choosing an appropriate parameter, which in my case is my m. Right, and we have seen a similar sort of technique when we were choosing k in my k nearest neighbor. So the same technique can be applied here just by looking at some theoretical background around it. And this technique is known as semi-parametric method, right? So this is known as semi, whatever you like to call it, parametric method. All right. So we have like theoretically arrived at some relationship between m and n, and this is like a good way to select m because that is going to bring your E out close to your E out star. And another way to choose a good m is by like something that's known as validation, and we're aware of that. And we'll talk more about that in a short while. All right. So this is one way of like creating a relationship between approximation versus generalization. Let's discuss a little bit about the VC dimension of the cascading effect that's there in a neural network. And it is going to be a short overview in classification. More detail is given in the textbook, but this should give you like a sketch of what's going on. So let's like quickly look at that. And let us assume we have like some input. Of course, I'm not like considering X, the entire thing. And then we have like this layer, the hidden layer. And this has like, this is a hypothesis set if you think about it, right? Each of the nodes, because this is like implementing a perceptron. And so H1, H2, and so on, maybe HM. Again, I'm sticking to like M nodes. And what happens is that we pick just one of these outcomes, right? So maybe I'm picking H1. Maybe I'm picking from this H2. Maybe I'm picking HM, right? And let's say the VC dimension of these like hypothesis sets is D1, D2, DM, right? And eventually we'll combine these, right, to get some final hypotheses. And this analysis is borrowed from the textbook, so you can go into further details. And see that this like VC dimension is DC, VC dimension of this hypothesis set, which eventually gives me my h of x. All right. So what this tells me is that like beginning from this x, right, I get this transformed to my h1x, h2x, and so on to hmx, right? And then my h of x, my final h of x is my hc of these whatever transformation I got from the previous one, right? So h1x, h2x, and so on up to hmx. Okay, so we are going back to some of the things that we did earlier when we were talking about the VC dimension. And so I'm asking the question, what is the number of dichotomies? Like what is the number of dichotomies that this cascading set can implement given like the VC dimension of each of these individual hypothesis sets? What is the number of dichotomies that can be implemented? Well, we'll have to look at like a pictorial sort of representation in terms of the input data, and let me do that on the next slide. So what's happening is my x1, this is my data, right? And xn, let's have n data points, right? And so my transformation works something like this. So I'll have like, as we wrote in the previous slides, I'm just like repeating it, but except my x is x1, right? h2, x1, and so on. Let me just end it here. x1, and here h1, x2, sorry, h2, x2, hm x2, and that's it. And this goes on and on until here when we get h1 xn, right? h2 xn, and so on, hm xn. All right. So as I said, how many dichotomies can be implemented on these n data points? And if you think about it, like one of these columns, like let's assume this first column, right? This first column is a dichotomy implemented by my hypothesis H1 on each of the data points, right? So if we look at like the total number of possible columns, we can like get by choosing H1 appropriately is at most like how many dichotomies can be implemented by each of these for n data points. Well, that is going to be like the upper bound of the VC dimension, which is n to the d1, right? So for this particular column, we can say that it is going to be n to the d1 because the VC dimension of this hypothesis set was d1. And so this is the VC dimension upper bound. Similarly, we'll have the same number for second column, right? And so on. So we'll have like n d m, right? And like if we change the columns, we get a different configuration of these n transform points. So then how many possible configurations are there for these n points? Well, let's say we are denoting them by some z's. So z1, z2 up to zm, right? And the total number of configurations is going to be the sum of these, which is like an upper bound, which is going to be like less than, and so number of configurations of z's, right, of these z's is going to be less than, and the sum of these essentially d1 plus d2 plus dm. Now that is pretty straightforward. Now, but like our problem doesn't end here because like we have another transformation hc. And how does that transformation work? Well, we would have done something here, right? And then we got some result. So the transformation that's applied to all these z's to get my h of c will give me a dichotomy on these z points, right? But then that dichotomy is also a dichotomy on my x's, my original x's, right? So finally, I'll have like these n to the dc because dc is the VC dimension of my HC. So we'll have like n to the dc ways to dichotomize my z1, z2, and so on to zm. Therefore, the total of my original question was what are the total number of dichotomies on these x's, my input data, right? So that is going to be the total number of possible configurations for my z plus what are the total number of dichotomies that are for like each of these z's. So that means the total number of dichotomies will be like there is an upper bound that is going to be n, right? N dc, which is like the VC dimension of the next one, plus the sum of like what we got here, right? So that sum is i's from 1 up to m nodes, right? And then di. All right. If we denote this entire summation by d, then we come to something that's known as like this is a lemma, and it's like explained better in the textbook, but I can give you an overview of what this tells us. And that lemma, by the way, states that like if we have n to the d less than 2 to the n, and my n is of the order some omega d log d, and after some algebra, basically how we arrive at this is like if n is greater than this like 2d log to the base d, and then my m, like the growth function, is less than 2 to the n, and my VC dimension for this comes less than 2d log d. You don't have to like get overwhelmed by the math, but just try to understand what is it telling us. That's, I think, sufficient. That's enough. So it is telling us it is possible to shatter some set of points, most likely some function md points, with m hidden units, and the upper bound can be loose by at most a logarithmic factor. So if n is large enough, then you cannot shatter all dichotomies, and so the VC dimension would be at most of the order summation di plus dc times like log summation di plus dc. As I said, no need to kind of get overwhelmed by the math. All we're doing is like the VC dimension of each of the nodes, the M nodes is like V1, V plus 1 M, and of the next layer is M plus 1, which is the same as like telling us this equation. And so essentially that's how we get to this equation. As I said, I'm not going to give you the exact proof, but this is how we get to this equation. For an MLP, this is the VC dimension. All right. So that was a high-level explanation of the VC dimension of the MLP and how cascading is more powerful. And what does that tell us about M and like the generalization versus approximation? Well, if we choose M small enough, maybe by using validation or something, we can control the generalization issue. We can keep things in control. Or maybe we use the theoretical way of keeping things in control. But you can tell just by looking at the VC dimension equation and the dependence of that on my M and D, how bad it can get, right? And or how good it can get, like depending on the choice of my M and other things. So now the next question that arises is like, we know that like this is a powerful model and it is going to overfit. And so we need some methodology to control that overfitting. And that's the next thing that we are looking at. So let's go to the next video and look at that.